Hello, my dear students. Welcome to PW English Medium Class 9th and 10th YouTube channel. My name is 𝐂𝐇𝐀𝐍𝐃𝐄𝐃. I'm your physics teacher. Students, in Phoenix batch, we left out with a last chapter in a physics, that is the sound. Okay. So, in this particular session, we are going to discuss in detail about a sound chapter. Okay. So, without wasting our time, let's get into the topic. So, today in physics, okay, in physics, we are going to discuss about last chapter that is a sound, and this chapter for a class 9th CBSE students. Okay, batch name you can see, that is the Phoenix batch for class 9th CBSE students. Okay, and this session going to be one short lecture. That means we are going to cover all the NCERT topic in one go. In this particular session, we are going to discuss very important parameters and important concept of a sound. Okay, so first we will be knowing what is a sound, nothing but a definition. Then how do you measure a level of a sound? That means a unit. Then production of a sound. Then how the sound can travel, that is the propagation of a sound. After that, what are the characteristics of a sound? That means if you want to differentiate a two sounds, okay, so there are a characteristics. With the help of those characteristics, you can differentiate two different sounds. Okay, then last one, reflection or echo of a sound. Then last one, that is hearing of a sound. Okay, hearing of a sound, that means the range of hearing. Got it? Okay, so let's start with the production of a sound. Okay, so before that, try to understand what is this a sound. Okay, what is this sound? So like light, heat. Okay, light and heat. Okay, light is a form of energy which gives a sensation of a vision to our eyes. Heat, it is also a form of energy which gives a sensation of hotness or coldness. Okay, and in the same way, sound is also a form of energy which gives a sensation of hearing. Okay, so sound is nothing but it is also a form of energy. Got it? And in this particular chapter, we are going to discuss about how sound produces and how sound propagates, means it travels in a different mediums like solids, liquids, and gases. And how about a vacuum? Okay, so first one, let's see what is the sound. So here you can see sound is the form of energy which causes or gives the sensation of hearing. Simple. Okay, it is a form of energy. What does it do? It gives a sensation of hearing. That's it. Okay, then what is the benefit of a sound? We can communicate. Okay, with the help of a sound, we can communicate. Sound help us to communicate. Next, how does this sound produces? Okay, how does this sound produces? By a vibrating. Okay, by the vibration, the sound is produced. For example, let's say, consider my hand. Okay, consider my hand. It is not in a vibration state. Okay, it is in a state of rest. Okay, with the help of external agent, that is my another hand. Now what I'll do, just I'll clap this one. So when I touch this one or clap, what is happening? At micro level, okay, when you see micro level, the particles on my hand, okay, the particles on my hand will be in a vibration mode. So due to that vibration, we are able to hear this clap. Okay, one more example. Okay, let's consider in front of me there is a table. Now you are not able to hear any sound because there is no vibration of particles of this table. Now what I will do is, with the help of my hand, okay, with the help of my hand, just I'll tap this one. You see, are you able to hear? One more time. So here you are able to hear a sound from the table. So in the first case, there is no vibration. Okay, there was no vibration. Due to that, there is no production of a sound. When I tap on the top of the table, you are able to hear a sound. Why? When I tap on the top of the table, I made a vibration of the particle of the table. So that vibration causes or produces a sound. One more example, let's consider here there is a one table and there is a one ruler, or else you can call it as a scale. Okay, so it is a metallic scale. Okay, not a plastic one, metallic scale or ruler. One end I'm keeping it on a top edge of the top edge, okay, of the table, and another end it is a free to move. Now what I'll do, so one end I'll be fixing, means it should not move, and another end it is a free to move. Now from a free end, what I'll do, I'll just disturb that table. Sorry, not a table. I'll disturb this end of the scale. Okay, by doing this. Now you can observe this ruler or this scale starts vibrates. Okay, starts vibrates. When it is vibrating, you can hear a sound. Okay, you can hear a sound. Let's consider one more example. Let's take a one rubber band. Okay, rubber. Let's take a one rubber. What you have to do is take one end in your mouth, okay, and with the help of your teeth you hold it, okay. Another end you just stretch it, okay, like this. And what you have to do after stretching, just pluck it with the help of your finger, and that rubber starts vibrating, okay, starts vibrating. Then you are able to sense it, that vibration you are able to sense it, and during that vibration of that rubber you are able to hear a sound. After stopping that vibration of that rubber, okay, after some time what happens, that vibration ceases, means it stops. After that you are not able to hear that sound. That indicates if sound is coming from any source, that means that body is in a vibrating mode. Got it? Okay. Then how do you measure a level of a sound? That is a decibel. Decibel means 1/10, 1 divided by 10. Okay. So now sound is produced. Okay. Sound is produced by vibrating body. So without vibration, the sound cannot be produced. Okay. The last one, sound is measured in terms of a decibel, and a decibel meaning is, okay, decibel meaning is 1 divided by 10th part, okay, 1 divided by 10th part. So that we call it as a decibel. Now, what do you mean by vibration? So I'm keep on, pronouncing one word, that is a vibration. Okay, vibrating body or vibrating, object. Okay, what is this vibration? To and fro motion of the body. Okay, here I have considered, a ruler or scale. When I disturbed this scale, it is moving up and down. So that means to and fro motion. Okay, and one more example, you consider a rubber. When I pluck it, it starts vibrating up and down. That up and down motion we are calling it as a to and fro motion, or else back and forth motion. Okay, back and forth motion, we call it as a vibration, or vibration of the particle or vibration of the body. Got it? So here you can note down, to and fro or back and forth motion of the body is called vibration. Okay, simple definition. Okay, simple definition. Now let's see a few more example of vibrating bodies. Okay, vibrating bodies, because we are going to discuss about vibrating part of a musical instruments. As our topic is a sound, we are going to discuss about a musical instruments as well. Okay, like which part of the musical instrument produces a sound. Okay, like if I consider a guitar, so which is the part of a guitar which produces a sound? We know that it is the string. In the same way, for other musical instruments, we have to check it. What is the part of a musical instrument that produces a sound or music? Okay, now, so let's see vibration of a body. So here there is a one image. Here you can see one boy holding a stick, one metallic, body that we generally call it as a pan. Okay, now metallic plate. So first step, what do you have to consider? Metallic plate. First step, that is a metallic plate. Okay, second step, hang it at a convenient place in such a way that it does not touch any wall. You have to take it, okay? This pan is tied with some string, okay? It can be, a cloth string or a metallic string also fine, okay? No problem. But try to consider it as a, cloth string. So tie this pan with a, string and just to hold it. Hang it, okay? After hanging, you have to take care this pan or metal plate should not touch with any walls. Okay. Now what you have to do? Just with the help of a stick, you just disturb by hitting it. Okay. Or you just strike the metal plate. Okay. Third step, what do you need to do? Now strike it with a stick. After that, what happens? Do you hear a sound? Yes, definitely. Yes. Definitely yes. Touch the plate. When you strike this pan and it will be vibrating. Okay. But you cannot see. But gently if it touch on the top of the metal plate, you are able to feel it. That vibration of the metal plate. Okay. Now here, touch the plate or pan gently with your finger. What you'll observe? Okay. What you'll observe? You feel the vibration. When you feel the vibration, yes, of course, after striking this metallic plate or metal plate or pan with a stick, after striking with a stick, it produces a sound. And if you touch this metal plate, you are able to feel that is the vibration of a metal plate. Okay. So what is the cause of that sound? It is simple, that is a vibration. Simple. Okay. Let's consider one more example. Here we have a box and two pencil and a rubber. Okay. So what you have to do? First step. Okay. First step. Take a rubber band, put it around the longer side of the pencil box. Longer side means like that. Okay. Longer side, not a shorter side. Longer side. Okay. Insert the two pencil between the box and the stretched rubber. Okay. So after inserting a two pencil, we have to stretch it. Okay. So that rubber becomes a stretched condition. After that, what you have to do? Now plug the rubber band somewhere in the middle. Okay. So you have to plug the rubber in the middle of that length. Okay. Now why only in the middle? For the better result. Simple. Okay. For the better result. If you want to hear pure sound, you have to plug that in the middle of that length. You can plug here also. You'll be hearing a less sound. Okay. And the third point, after that, what you have to do? Plug the rubber band somewhere in the middle. Then when tightly stretched hand is a plucked. Okay. Band. This is a band. Okay. Is a plucked. It vibrates and produces sound. Yes, of course. When you pluck it, the rubber starts vibrates. Okay. And produces a sound. Okay. And after some time, that vibration keep on decreases. Finally that vibration ceases, means stops. Then you are not able to hear any sound from the rubber. Okay. So this is also indicates, okay, this is also indicates the sound producing body is always vibration state, is in always vibration state. Got it? Now let's consider one more example with a one plate and one spoon and water inside it. Okay. Okay. Right. Now first, what do you have to do? First, take a metal dish or else a plate, pour water in it. Okay. You have to pour water in it. And the second step, what do you have to do? Strike it, its edge, means on the top. Okay. Looks like a rim, right? So you have to strike it with a spoon, with the help of a spoon. You will hear a sound, definitely. Both are metal. Okay, both are metal. When you strike that, rim of this, a plate, or else you can say it is a edge of the metal dish. Okay, you will hear a sound. Okay. And what is the observation you have to make? Yes, of course, sound is coming out from the metal dish or else a plate. Again, strike the dish and then touch it. Okay. After striking with the spoon, just keep that spoon aside and touch that metal surface. Okay, that is a metal dish. You'll feel the vibration. You may not, see the vibration of that metal dish, but you are able to feel the vibration of a metal dish or else a plate. Okay, and next one, strike the dish again. Okay, again take the spoon and again strike it. Look at the surface of water. Okay, so after striking with a spoon, okay, and water in the metal dish, okay, you have to observe the surface of the water, and that surface will be in a vibration, okay, the surface of water. And what you'll see, vibrating dish produces a waves in a water. Okay, that is nothing but a vibration in a water. Waves you can see, not so much so large waves, a small amount of waves you can see. Okay, so this is also indicates vibrating bodies produces a sound. Okay, now next one, next example here, let's consider this as a homework. Okay, let's consider this as a homework. First step, what do you have to do? We see that vibrating object produces a sound. Yes, of course, the last 3 to 4 examples we have seen. Okay, vibrating bodies produces a sound. In some cases, the vibrations are easily visible to us. Okay, like, a rubber as well as, metal, this one, metal scale or ruler. We are able to see that vibration of the body. Okay, in some cases, you will not be able to see that vibration of the body. Okay, now to us, but in most of the cases, their amplitude is visible. Amplitude means the maximum displacement of that body. Okay, maximum fro, okay, up and down, to and fro motion. Okay, up and down or to and fro motion from mean position. Okay, if I disturb this metal surface, okay, means a metal scale. Okay, this is the another edge and this is affixed with a table. Okay, so when I disturb this is the mean position. Okay, if it is going down, so from mean position, what is the displacement of the ruler? So that height or that depth we call it as a amplitude, or else again it move up. So this is the mean position, means when it is at rest without disturbance. Okay, and it is moving up, this is the maximum displacement of this. Okay, so from mean position, this is the maximum displacement of the body. That maximum displacement we call it as a amplitude of the body. Got it? Then their amplitude is so small that we cannot see them. However, we can feel them, like metal dish, water surface. Okay, those are the example where you are able to you are not able to see the vibration of the bodies, but you are able to feel the vibration of the bodies. Got it? And second task, okay, task we have to do it. Take a hollow coconut shell and make a musical instrument, iktara. What is this, a musical instrument? Yuktara or else iktara. Okay, and third step, what you have to do, you can also make it with the help of earthen pot. Okay, with the help of earthen pot. And the fourth point, what you have to do, play this instrument and identify it's a vibrating part. Okay, vibrating part you have to identify. Okay, so out of this system, okay, which is the vibrating part? Yes, of course, sound will be produced by this musical instrument, but what is the part which is producing the sound? We have to identify it. Okay, so let's see how many of you are able to identify that vibrating part of this musical instrument. Okay, now, so there are some musical instrument and their vibrating body. Okay, there are some musical instrument and their vibrating parts. Okay, the first one you see, veena. And what is the vibrating part of that musical instrument? Stretched string. Okay, and here you can see veena. Yes, this is the veena. Okay, now this is the vibrating string, and here also vibrating string, and here violin, and here tabla, here the small drum. Okay, here also tabla. So let's see, sitar, stretching string here also, and violin stretching string. So these are the sound producing part of the musical instruments. Okay, now tabla, it is a membrane. Okay, tabla, it is a membrane, stretched membrane. Okay, next one, mridangam, stretched membrane again, And the next one, drum. Here also stretched membrane. Next one, Shannai, air column. Okay, in a wedding and all, you are able to say that Shannai. And a flute, again air column. And mouth organ, again it is the air column. Okay, so let's see images of all these musical instruments. Okay, these are the musical instruments. Okay, these are the musical instruments. Here stretched string, here stretched string, here stretched strings are the part of the musical instrument that produces a sound. Okay, here membrane, stretched membrane, here stretched membrane, here stretched membrane. Got it? So next one, you see, this is Shannai. So what is the part? Okay, what is the part which produces a sound? Means this is the air column. Okay, so it looks like a pipe, that is nothing but an air column. By opening and closing these holes, we can produce a music. Okay, so here also mouth organ, mouth organ, so that is also air column. And here a flute, that is also produces a sound. Here just you have seen Iktara, and here earthen pot. By this also we can produce a sound. Okay, right. So this is all about a musical instrument and their images and their sound producing a part. Okay, now let's move on to the next concept, that is a propagation of a sound. Okay, sir, we got to know what is sound. Sound is nothing but a form of energy. And what is the unit? It is the decibel. Okay, how the sound produces? Due to vibration of a body, the sound will be produced. And how sound can be propagated means how sound can travel? Question mark. Okay, to answer this question, we have a very good example. Okay, very good example. So here we have one very good example. Let's see step by step. Okay, first step, what you have to do? We have to check how the sound propagates or how sound travels. Okay, so first take a metal or a glass tumbler, means it is a glass. Okay, metal glass or normal glass. Make sure that is a dry. Okay, make sure that a glass tumbler should be dry. It should not be wet. Okay, and place a cell phone in it. You can ask, sir, why should it be a dry? Why can't it be wet? Because when you keep a mobile, it is an electronic device. Okay, so due to water or a liquid, what happens to that cell phone? May get damaged. So that is the reason that a glass tumbler should be dry. Okay, now, so you have taken a mobile or cell phone, kept it in a glass tumbler. First step, it is a clear. Next one, ask your friend to give a ring on the cell phone. Yes, from another cell. Okay, you'll ask. Okay, you and your friend doing this activity. Okay, just imagine like that. So what you'll do, you'll take up one cell phone and keep it in a dry tumbler, means a glass, and you'll ask your friend to call to your number. Okay, your friend will call. And what happens when your friend calls to your cell phone? The cell phone starts ringing. Okay, listen to the ring. Okay, carefully. Then a fourth point, now surround the rim of the tumbler. So first what you'll do, first case. So you'll take a tumbler, glass tumbler, and it is a dry, and you'll keep your cell phone inside the glass tumbler, and you'll ask your friend to call to your number, and your friend will call to your number, and that cell phone starts ring, and you're able to hear that sound. Okay, now second case, what you'll do, surround the rim of the tumbler with your hands like this. Okay, like this. Okay, you'll be holding like this. Okay, then put your mouth on the opening between your hands. As you're holding your glass tumbler like this, right? So you have to put your mouth in this way. Okay, there should not be escaping any air. Like that, you have to take care. Now, what do you have to do? After put your mouth on the opening between your hands, indicate to your friend to give a ring again. Okay, what you'll do after arranging this one? Okay, you'll take a tumbler and you'll be holding Okay, your hands like this, and you'll be keeping your mouth like this. Okay, getting my voice? Yes. So you're able to see, or you're able to notice some changes in my voice, right? Okay. In the same way, what you'll do, you'll ask your friend to call again, and your friend will be calling to your cell phone. Again, it starts ringing. So first, you are able to hear a large sound. That means the loudness is more. So what you have to do, you have to remove air from the glass tumbler. Okay, remove air from the glass tumbler. How to remove that air? By sucking from the glass. Okay, so you have to remove that air from the glass. So here, listen to the ring while sucking air from the tumbler. Okay, and you will notice, okay, that decreasing amount of the loudness of a sound as air is coming out. Okay, as amount of air decreasing in the glass tumbler, the level of a sound, or else you can say loudness of the sound keep on decreases. Okay, now decreasing amount of air in the tumbler is the responsible to decreasing loudness of the ring. That means more the air means a medium. Okay, more is the loudness of a sound. Okay, simple case. Let's consider one more example and continuation of this. Okay, after removing entire air from the glass tumbler, okay, still the cell phone is ringing, but you will not able to hear that sound from the cell phone. What is the reason? As you completely removed air from the glass tumbler, that means there is nothing, even air particle is also not present. So the place, it is a completely empty. That empty space only we are calling it as a vacuum. Okay, so this term we will be keep on using in a physics. What is vacuum? Vacuum is nothing but it is a empty space where the air particle, even air particles are not present. Okay, so here you are not able to hear any sound. Okay, so this is which step? 9 and 10th step, and this is the 11th step, and this is the 12th step. Okay, 11th step. 10th step, let's see one more time. When air has been removed completely from the vessel, it is said that there is a vacuum in the vessel. So vacuum nothing but it is a completely empty. Even air particles are not present. Then sound cannot travel through the vacuum. Why? So as air decreasing, finally there is no air particle only. You are not able to hear anything. So that empty space we are calling it as a vacuum. We conclude that, okay, if there is a vacuum, the sound cannot travel through it. Simple conclusion from this activity. Okay, sound needs a medium to travel. Sound needs medium to travel. These 2 points are very, very important for your exam point of view. Okay, so to propagate or for the propagation of a sound, there must be a material medium. Maybe it is a air medium, maybe it is a liquid medium, maybe it is a solid medium. Okay, but it cannot travel through the vacuum. Let's consider one more example. Okay, space. In the space, okay, astronauts will be hearing space suit, and they cannot talk directly. They'll be having or walkie talkies. Okay, what does that walkie talkie do? See, walkie-talkie that converts your sound energy into electromagnetic waves. Sound waves into electromagnetic waves. That electromagnetic waves from your walkie-talkie will be transferred to your friend walkie-talkie. Just imagine you both are astronauts in the space, okay? So you have to communicate something. What you'll do, you'll speak through the walkie-talkie. So that walkie-talkie, it will convert the sound waves to electromagnetic waves. That electromagnetic waves will travel to your friend. So that walkie-talkie will receive that electromagnetic waves, again convert that electromagnetic waves into sound waves. So that's how in the space, you both can communicate. Directly you cannot communicate because there is nothing. It is a completely empty space. That is a completely vacuum. So that is the reason, in the space, through the walkie-talkie, astronauts will be communicating. Got it? In the space, nothing but, let's consider one more example. On the surface of a moon, you cannot talk directly. What is the reason? Because on the surface of a moon, it is completely empty. There is no atmosphere. Atmosphere means air particle. There is no air particle at all. So on the surface of moon, sound cannot propagate. Okay, if you want to communicate something, you have to use, walkie-talkie that converts your sound signal into electromagnetic waves, and electromagnetic waves again converting into a sound signal. Got it? So for ninth class, what you need to remember? So first point, this is the first point you have to remember. Through the vacuum, the sound cannot propagate, and for the propagation of a sound, it required a material medium. Simple, okay? Now, so here we have a scene, air, by considering air, nothing but gaseous state. Let's consider another case, okay, bell jar experiment. This bell jar experiment that shows, okay, bell jar experiment that shows sound, okay, sound needs a medium to travel, okay, that is a material medium to travel. Material medium is required for the sound to propagate. Maybe it is solid, maybe a liquid, maybe gaseous state, but it cannot travel through the vacuum, okay. By this experiment also you can conclude sound cannot travel through the vacuum. These 2 points are very, very important, okay. So there are 2 conditions. Let's see, here air present, okay, this is a glass jar, and when air is present, this boy is able to hear bell sound, okay. So in this case, vacuum, no air is present, still the bell is, moving, nothing but vibrating, but this boy is not able to hear any sound, no sound heard, because it is a vacuum, no air, nothing but it is a vacuum. Got it? Now, so this entire setup we call it as a glass jar experiment. What is the benefit of this glass jar experiment? It shows that, for the propagation of a sound, material medium is required, and the sound cannot propagate through the vacuum. That's all. 2 points are very important. Next, sound can travel through the solids and the liquids, okay? Solids and the liquids. So already we have seen gaseous state by taking an example of a glass tumbler and a cell phone, and you as well as your friend, right? Now let's consider a next state, that is the solids and the liquids, okay? Now first, what you have to do, look at the diagram carefully, okay? Look at the diagram carefully, and let's consider yourself, okay? You and holding a bell, and this is a container which is containing a water. Let's consider it as a water, okay? So first, what you have to do, take a bucket or bathtub, okay? Let's consider a bathtub or a bucket, whatever you want. Next, fill it with a clean water. Why it is a clean water? Because to see that movement of a bell, okay? Next one, take a small bell in one hand, okay? You have to take one bell in one hand, okay? And the next step, what you have to do, shake this bell inside the water to produce a sound. So when you shake the bell, what happens? Inside there is a one small metal, and due to a movement, what will happen? This small metal will strike this surface of the bell, and it produces a sound, okay? Now, make sure that the bell does not touch the body of the bucket or bathtub, okay? And it should be in the middle, and it should not touch with the walls of the container, okay? Next, place your ear gently on the water surface, okay? You will hear the sound. Thus sound can travel through the liquid. This is the experimental result, okay? This is experimental result, so which shows the sound can travel through the liquid as well, okay? Now, so first gaseous state, it is completed. Next one, liquid state, it is by considering a water, clean water. Now let's see the next example, that is a pipe, okay? Look at the diagram. You and your friend, let's imagine you and your friend, there is a one metal, okay, or else one solid. So first, what you have to do, first step, take a meter scale or a long metal rod and hold its one end to your ear like this, okay? Like this, as you hold your mobile phone, right? So like that, okay? So you have to ask, okay? You have to ask your friend to gently scratch or tap at the other end of the scale, okay? you'll be holding one end near your ear and other end will be holding by your friend. You will ask your friend to scratch at other end, and what will happen? You hear the sound of the scratching. When your friend scratches at the other end of this, you know, what is this? Maybe it is a solid, okay? Or else you can consider it as a meter scale. So when let's consider a meter scale only. So when your friend scratches at the other end of a meter scale, you are able to hear that scratching sound, okay? So that means the sound is also traveling through the solids. So that means sound can travel through the solids, sound can travel through the liquids, sound can travel through the gas state, but it cannot travel through the vacuum. Okay, right. Last point, sound can travel through the any solid. Next one, yes. So now we know definition of a sound. It is nothing but a form of energy which gives the sensation of a hearing, and unit is a decibel. Okay, and how does the sound produces means by vibration of a body. And the next one, okay, next one, propagation of a sound. If the sound is a producing and it has to propagate to reach our ears, right? So in the form, okay, so propagation of a sound, it can travel through the solids, liquids, as well as a gas. Here our question is, sir, you're talking, just imagine our physical classroom. Okay, let's consider our class 9th classroom. Okay, just imagine I'm teaching this lecture to your class. I'm discussing about different topics and you're able to hear my voice, right? Here I'm talking, okay, and my voice is traveling from this position to your till your ears. Okay, so in the water form, okay, in the water form, sound is a traveling. Okay, sound is a traveling. Yes, of course, it is traveling through the medium, that is the air. Okay, but in the water form, that is a wave. Okay, sound wave. Sound is the traveling in the form of a wave. Then what is this wave? Wave is nothing but transfer of energy. What is that energy? Sound energy. Okay, here I'm talking. Let's consider our physical classroom. Here I'm talking and my energy in the form of a sound. Okay, so here wave. Wave is the form of energy. It is transformed from one position to your position without actual transfer of a matter. Myself considered as a matter. Okay, source. Sound producing a source. Okay, I am producing a sound, and my sound is reaching your ears without actual transfer of myself. Myself means myself as a matter. Okay, so that means wave is nothing but it is the energy, transfer of energy without actual transfer of a matter. That's all. Okay, waves are two types, two categories. Okay, one is mechanical wave, another one is non-mechanical wave. Let's see what is this mechanical wave and what is non-mechanical wave. Okay, so first, wave. What is this wave? Already I have informed, or else I have given definition of this wave. Wave is the energy transmitted without actual transfer of a matter. Okay, so waves are two categories. Okay, the first one is a mechanical wave and the second one is a non-mechanical wave. So what is this mechanical wave and what is this non-mechanical wave? Okay, so mechanical wave means the wave, okay, waves requires or wave needs a material medium for the propagation. For the propagation. And what about this one? Second one, non-mechanical, opposite. The wave do not required. Okay, the wave do not require material medium okay, material medium for the propagation. Okay. So example for mechanical and non-mechanical wave. Mechanical and non-mechanical wave. Example, sound. Okay. Sound is the form of energy, and sound is propagated in the form of a wave. And this wave required a material medium to propagate. Example, okay, maybe it is a solid, maybe it is a liquid, maybe it is a gaseous state. Already we have seen the examples also. Example here you can consider mechanical wave, it is the sound, okay, sound wave. And example for non-mechanical wave, it is a light. Sir, how light can be a non-mechanical wave? Non-mechanical wave, it does not require any material medium. Means it can travel through the vacuum also. It can travel through the vacuum. Let's consider an example. Where do we get a light from? Okay, where do we get a light on the surface of earth? From the sun only, right? Answer is sun. So between sun and earth, there is nothing. It is completely empty space. Okay, by traveling a large distance, the light from the sun and reaching the earth's surface. Between this earth as well as the sun, there is nothing. It is completely vacuum. That means light do not, okay, require a material medium to propagate. So best example for non-mechanical wave, okay, light wave, because light do not require material medium to propagate. It can travel through the vacuum as well. Okay, right. And same wave based on a propagation, okay, based on a propagation, it is divided into two categories. The first one, it is a transverse wave. Second one, a longitudinal wave. Let's see what is that transverse wave and a longitudinal wave. Okay, now already we know that what is a wave. Okay, wave is nothing but a transfer of energy without actual transfer of a matter. So this wave based on direction of propagation of a wave and particle, here we have two categories. One is transverse wave, another one is longitudinal wave. Okay, try to understand the individual particles of the medium. Maybe it is a solids, maybe it is a liquid, maybe it is a gases. The individual particles of the medium move about their mean position in the direction perpendicular to the direction of wave propagation. Okay, what does that mean? One more time you see, the individual particles of the medium can be solid, liquid, gas, move about their mean position in the direction perpendicular to the direction of a propagation of a wave. Means, for example, this is the direction of a wave. Okay, let's consider this is the direction of a wave. And the direction of a propagation of a particle, like this, up and down. Okay, so this is propagation of a particle, and this is the wave. And what is the angle? 90 degree. And what is the angle? 90 degree. Okay, so when angle between, particle motion and wave motion, if it is the 90 degree, then you can call it as a transverse wave. And example for transverse wave, here you can consider light. Okay, again light wave, But what about here? Here a 90 degree, opposite to this transverse wave. 90 degree opposite, it is a 0 degree. Let's consider it as 0 degree. The particle motion and wave motion, if it is the same direction, then you can consider it as a longitudinal wave. Okay, for example, let's consider this is the wave motion. Okay, this is the wave motion. This is the wave motion. Okay, this is the wave motion. Okay, this is a wave motion, and this is particle motion. Particle motion. And here, this is particle motion. What is the angle? What is the angle? 0 degree. Nothing but parallel. Okay, 0 degree. Nothing but parallel. Then you can call it as the longitudinal wave. Okay, I'll show you with simulations. Okay, very good simulations. the individual particles of the medium move in the direction parallel to the direction of a propagation of a disturbance. Disturbance is nothing but a wave motion. See, this is the wave motion, and particle motion is also along the wave motion. That is a parallel to the wave motion, or else a disturbance, right? Then this exactly how sound wave propagates. Therefore, longitudinal wave example is a sound wave. Okay, so let's see. In a best way, we can see the simulations. Okay, so let's consider. Yes. Let's try to understand. See, this is a transverse wave. Okay, is it visible? Let me reduce the brightness. Yes. You see, this is the particle motion. Okay, this is the particle motion, and the wave is moving in this direction along plus axis, and the particle motion is up and down, up and down. See, this is the particle motion. Try to understand. This is the particle motion, up and down, up and down, up and down. But wave motion this way means the particles how they move in this way, up and down, 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 up and down. Like that, the particles will be moving. And this is the wave motion and the particle motion along y-axis and the wave motion along x-axis. So this kind of arrangement of wave motion and particle motion, we call it as a transverse in nature. And what about the longitudinal? You see, one more example. Yeah, this is the best example. Yeah. You see, the particles moving along x-axis and the wave is also moving along x-axis, right? Wave is also moving along x-axis. So wave motion and particle motion, if they are in the same direction, you can call it as a longitudinal waves. Okay. Best example for the longitudinal waves, that is the sound waves. Okay. And please concentrate on this red color as well as the green color. Okay. Note. Okay, red color and green color. See, just they are vibrating, means they do not move forever. So just they are moving forward and again backward, forward and backward, forward and backward. So this movement we call it as a vibration. So here vibration of a particle and wave motion is along the same direction. That means parallel to each other. So this arrangement we call it as a longitudinal wave. Got it? Okay. Now, right. So this is the diagram. Okay. So this is the transverse wave and this is the longitudinal wave. What you have seen in the simulations. Okay. Now, next one, terms related to wave. So here there are two waves. Okay. Transverse wave and a longitudinal wave. So here we have to define with respect to longitudinal wave, because our chapter name, it is a sound. So with respect to sound, we have to define the terms. Sound wave is a longitudinal wave. So let's consider a longitudinal wave. Okay. So here you can see the coil. Okay. Here number of coils you can see. If you consider one coil and a number of coils, okay, arranged in this particular path. So here you can see number of coils, they are very close to each other. Okay, they are very close to each other. Okay, so this arrangement we are calling it as a compression. Means when the space between each coil is less, or the each coil are arranged very closely, then you can call it as a compression. If the each coil have enough distance, enough separation between each coil, you can call it as a rarefaction. Okay, so compression and rarefaction. You see, here the distance between each coil is very, very small, and distance between each coil is very, very large comparatively. Therefore, if the distance between each coil is small, then you can call it as a compression. If a distance between each coil is large, then you can call it as a rarefaction. So, a longitudinal wave can travel in the form of rarefaction and compression. Compression, rarefaction, compression, rarefaction, compression, rarefaction. Okay? And the distance between, okay, the consecutive distance between compression and rarefaction, we call it as a wavelength. Okay, the distance between compression and rarefaction, we call it as a wavelength. You see, This is the compression and this is the compression. Okay, you can consider a compression. That means two consecutive, okay, the distance between two consecutive compression or rarefaction. We call it as a wavelength. Okay, you can call it, consider either compression or rarefaction, both are same. Okay, so if you want to define, okay, if you want to define that wavelength in terms of a compression, how do you define? Okay, how will you define? So here you can define, okay, the distance between the conjugate, okay, the distance between two consecutive compression is called wavelength, or else the distance between two compression or rarefaction, the distance between two rarefaction is also called a wavelength. Getting my point? So now already we have defined a compression, rarefaction and wavelength. Okay, let's see next one. Yeah, the reasons where the coils become closer is called a compression, that is represented by C, and the reason where the coils are further apart means that the distance between each coil is more, you can call it as a rarefaction, R. Okay, now next one, the peak is called crest and valley is called trough. This is not related to, you know, longitudinal wave. This is related to transverse wave. Okay, this is related to transverse wave. This is related to transverse wave. Okay, now what is this crest and trough? See, this part, upper part is called crest. Okay, upper part is called crest and lower part is called trough. Okay, clear? Now, yeah, amplitude. What do you mean by amplitude? See, this is the, here you can see arrow mark, right? So this is the maximum displacement of the particle. Okay, the maximum displacement of the particle from mean position. Like a scale and a ruler, we have considered example, right? From rest position is nothing but a mean position. If you vibrate, okay, if you disturb that scale, it will move up and down, right? So from mean position, what is the maximum displacement? And from mean position, what is the maximum displacement? Up as well as the down. Okay, either side you can consider. Maybe you can consider up or you can consider it down. Okay, so that maximum displacement we call it as the amplitude. That's all. Okay, now, yes, the magnitude of a maximum disturbance or a displacement. Okay, maximum disturbance or displacement particle of the medium on either side of the mean value is called amplitude of the wave. It is usually represented by letter A. Okay, and SI unit, as we are talking about a displacement, what is the SI unit of a displacement? Displacement is again, it is the form of a length, right? It is again a form of a length. So how do you measure a length in a SI unit? That is a meter. Therefore, SI unit of a amplitude, okay, SI unit of a amplitude, that is a meter. That is represented by small letter m. Okay, right. Next one, wavelength. Already we have seen. That is the distance between two consecutive compression or two consecutive rarefaction is called a wavelength. That is in terms of a longitudinal wave. If you want to define this wavelength in terms of a transverse wave, you can define this one as, you know, the distance between two consecutive crest or trough is called a wavelength. Okay, simple. So the distance between two consecutive compression or two consecutive rarefaction is called a wavelength. So wave a length, again you are measuring a length. Therefore, SI unit, again it is a meter and represented by small letter m. Okay. Now next one, a frequency. What is this frequency? Okay. For example, let's consider a ruler case only. Okay. Scale, meter scale. So when you disturb that one, okay, it will vibrate up and down, right? So in 1 second, how many times it vibrates? Okay, in 1 second, how many times it vibrates? That number of vibration per unit time. What is the SI unit of a time? That is a second. Okay, so in 1 second, how many number? Okay, how many times means number. Number of vibration per unit time is called a frequency of that wave. Okay, the number of compression or a rarefaction. So here vibration I used for a transverse wave, here compression. The number of compression or rarefaction per unit time is called a frequency. Okay, means to say this. See, let's consider this is a compression, right? Where the lines are very close, we call it as a compression. Where the lines are apart, okay, coils are apart, then we can call it as a rarefraction. So in 1 second, how many compressions or how many rarefractions in a per second, okay, per unit time, that is in 1 second, that number of compression or rarefaction, we are calling it as a, frequency of a wave. Got it? Okay. And here, the number of a compression or rarefaction per unit time, okay, per unit time is called a frequency, and this frequency is given by F. Okay, SI unit, you see, hertz. Generally it's given by hertz, and symbolically, okay, symbolically we represent Hz. There is another unit of this, okay, per second, okay, per second. Per second means per second. You can write like this, or per second like this. This is the unit, and this is symbol of unit. Got it? Now, next one, time period of the wave. Okay, what is this? Time taken by, okay, time taken by the wave, okay, time taken by the wave to complete its one vibration in case of a transverse wave. And in case of a longitudinal wave, it is the time taken by a two consecutive compression and rarefraction is called a time period of a wave. Okay, now, time taken by two consecutive compression or rarefraction to cross the fixed points. Fixed point means this one. For example, let's consider this is the fixed point. Okay, this is the fixed point. So here, time taken by the from here to here. Okay, from here to here. So what is the time taken by this compression to cross this red line? Okay, or else let's consider these are the 2 points. Okay, these are the 2 points. Let's consider compression moving and crossing that green line. Okay, crossing that green line. How much time this compression has taken? So that we call it as a time period of that wave. Not only for compression, you can consider a rarefraction also. Okay, and here you can see rarefraction from here to here. Okay, so this is the rarefraction. Okay, the distance between lines, it is a more compared to the previous one. So time period is nothing but time taken by a compression, two consecutive compression or rarefraction is called time period of the wave. Okay, so let's see one more time. This is the reference point. One compression has crossed, another compression has crossed this green line. So two consecutive compression or rarefraction. Then what is the time interval between them? Then it is a time period. Okay, right. Next, and a time period, as we are talking about a time, then it is a second only. Then it is a second only. SI unit, second. And represented by yes. Okay. Now next one, characteristics of a sound. What is this, the characteristics of a sound? Okay. So if I say hi, you also say hi. And entire classroom will say individually hi, hi, hi. Okay. How do you differentiate my sound, your sound, and your classmate sound? And what parameters you can differentiate our sounds? Okay. So here there are some characteristics of the sound. With the help of those parameters, we can differentiate our two sounds. So let's consider myself as well as you. Okay. The wordings are same. For example, hi, hello, good morning. You will also say hi, hello, good morning. So here statement is same, but a sound will be different. Sound, nothing but voice will be different. So with the help of what parameters we can differentiate it's a my voice or else your voice. So there are three characteristics of the sound by which we can differentiate our two sounds. The first one, loudness. Second one, pitch. Third one, quality. It is not there for your syllabus. So let's talk about the first two. The first one, loudness, and second one, a pitch. Okay. So let's talk about that, loudness and pitch. Okay. So loudness. Okay. Let's consider two identical drums. Okay. A drum and B drum. So I'll take a small pencil. I'll strike that drum A. And I'll take one big stick, I'll strike that drum B with the same amount of a force. Which one produces a large sound? Definitely the second B, because it is the largest stick. I mean, bigger stick. Okay. Or else let's consider same stick. Okay. Let's consider same stick. Drum A and drum B. Okay. So drum A, I'll be striking with the help of 10 Newton, and drum B with the help of 20 Newton. Which one will make a more sound? Definitely the drum striking with a 20 Newton, because of more force, more is the sound. So here loudness is nothing but it is the amplitude of the wave. But how do we get to know amplitude is more or less? Let's try to understand one situation. You have to take a thermocol balls, okay, keep it on the surface of drum, okay, and the rest before hitting that surface, okay, drum surface, nothing but a membrane, stretched membrane, okay. So all the thermocol balls will be lying on the surface. When you strike with a stick, what will happen? When you strike, the sound will produce. At the same time, the thermocol balls will raise up, okay, raise up. So from the surface, how much height they'll raise, that indicates an amplitude. Okay, that is indicating amplitude. So let's consider two examples. I mean, two drums, A drum and B drum. So same amount of thermocol balls on the surface of A drum, same amount of thermocol balls on the surface of B drum. Okay, but the condition is the first drum is struck with force of a 10 Newton, and the second one with a force of a 20 Newton. As the force is more in the second case, at the same time, if I strike both the drums, in both the cases, you can see the height raised by those thermocol balls. So it will be height if we compare from the surface of those drums, the drum A, from the drum A, the thermocol balls will raise compared to the uh, thermocol balls from the surface B, that is the drum B. So here you can consider, if we compare the height of thermocol balls, okay, the thermocol balls of height in a case of drum B is a more compared to the first case. And also you can hear a more sound from the drum B, because you have striked with a 20 Newton force. That definitely the sound, nothing but a loudness of drum B is a more compared to the drum A. Here what you need to understand, and which topic you need to pay attention. Here just amplitude, nothing but a displacement of the particle, nothing but a thermocol balls from the surface of a drum. Okay, so loudness is directly proportional to the amplitude. Okay, now the first term, okay, characteristics of the sound, loudness. What is this loudness? Loudness of a sound. Okay, loudness is the characteristic of a sound by virtue of which a loud sound can be distinguished from a faint sound. Okay, loud sound is distinguished from a faint sound, both having the same frequency and the same waveform. Okay, frequency already we know that. Okay, so frequency is nothing but number of vibration made by the particle per unit time. And what about this waveform? Waveform means shape of the wave. Okay, shape of the wave, right? What is the shape of the wave? Okay, generally we consider it as sine wave. What is that sine wave? I'll show you. Okay, and this will be the sine wave. Okay, right? So this is the sine wave, this is the shape or else waveform. Got it? And the second example you can see, example for this loudness of the sound. If we gently pluck the string of a sitar or a guitar, a soft or faint sound is a heard. Okay, faint or soft sound is a heard. But if you pluck the string hard, it gets displaced more from its rest position. That is amplitude. This term is very important. Okay, of vibration increases, so loud sound is heard. Therefore, loudness of a sound is directly proportional to the amplitude. Okay, directly proportional to the amplitude. And this amplitude square. Okay, so generally we write it as a amplitude square. Okay, so next one, that is example 2. If you strike the drum gently, a faint sound is heard. But if you strike it hard, you hear a loud sound. Okay. Here also, loudness is directly proportional to the square of the amplitude. Okay. And the next one, pitch. Pitch is nothing but a shrill and a flat sound. If you want to differentiate a shrill and a flat sound, this pitch plays very important role. And what is this pitch? Pitch is also, it is the characteristics of the sound. Here you are able to differentiate two sound, that is a shrill as well as a flat sound. Okay. So example for a shrill sound, okay, voice of a baby, or else during the cry of a baby, that is a shrill sound. Okay, so crying of a adult as well as the crying of a baby, small baby, you are able to differentiate. Shrillness means number of vibrations per unit time. Vocal cord vibrates, right? So in case of a small baby, it is a more compared to the adult one. Okay, so that is the reason crying of a small baby is a more shriller than a adult cry. Okay, right. So what is this pitch? Definition wise, it is the characteristics of sound that differentiates acute or else shrillness of a sound or shrill sound from a flat. Loudness, it is a differentiate faint sound with respect to loud sound. Okay. Now, it depends on the number of vibration. This shrillness of a sound depends on, depends on number of vibration per second, nothing but a frequency. Okay. So here I'll say loudness depends on the amplitude of the wave, and the shrillness, this shrillness of the sound, nothing but a pitch. Pitch is depends on frequency, okay? Frequency of a sound. Frequency of a sound, okay? Right. Sound each, okay. Pitch refers only to the musical sounds, okay? This pitch is only refers musical sounds, okay? Each musical note has a definite pitch. If the pitch is high, the sound is shrill, and if the pitch is low, the sound is a flat. Examples you can see. Examples for a pitch. The frequency of a sound of a crying baby is a more than that of a crying adult. So the sound of a crying baby is a shriller than that of a crying adult. Already I have a given example. The next one, the voice of a female is a shriller than that of a male. Okay, so here you can consider voice of male as well as a female. Okay, so these are the best example for pitch, right? Next, so here you can see characteristics of the sound. So first one, loudness, here you can see. So frequency and here amplitude. So first consider a loudness of a sound. Loudness of a sound depends on amplitude square. Okay, so amplitude, here you consider height of the wave, here height of the wave comparatively. Okay, so here height of the wave is a very small and here height of the wave is a large comparatively. Okay, so that means here you can say this is a louder. Okay, this is a louder. Second case, it is a louder. Okay, this is the louder and this is a quieter, means it is a faint sound. And here frequency you see in a same given time, number of vibrations. Okay, here you see 1, okay, 1, 2, 3. 3 times it is vibrated. Okay, there is a 3 times vibration in a per given time. Okay, now in this case, in a same given time, 1, 2, 3, 4, 5, 6. Here just 3 times, here 6 times. That means the number of vibration in the second case is more. Therefore, pitches depends on vibration. Frequency. Frequency depends on number of vibration. Here in the second case, more number of vibration. Therefore, pitch is more. Higher pitch, and this is a lower pitch. Okay, now let's consider a speed of a sound in a different mediums. Okay, you just go through all these examples: solids, liquids, and gases. Okay, right. Next one, a speed of a sound in different mediums. This is solid, this is a liquid, and this is gases. And all these data is not unnecessary. For your information, I have considered. Okay, so I have given this data for your information. In examination, they do not ask. Don't worry. Okay, now next one, question we have to solve. The question 1, example: sound wave has a frequency of 2 kilohertz and a wavelength 35 centimeter. How long will it take to travel 1.5 kilometer? Okay, so relation between So first I'll explain the concept, okay? Concept. What is the concept? Yes. Relation between speed, frequency, and wavelength. Already we know that all the definitions, wavelength and frequency, speed of the sound wave, okay? The relation between speed, frequency and wavelength of a sound wave, of sound wave, okay? It is given by, it is just a formula, V is equals to F lambda. V is equals to F lambda. V is equals to F lambda, where V means speed and frequency means F and wavelength means lambda. Okay, so it's the same concept. Here they have a given. First we need to write down data. So data, okay, so first we need to write data, and by the data we can say that frequency, it is at 2 kilohertz, okay, 2 kilohertz, but it is not in SI unit, therefore we have to convert that, okay. Kilo means 10 power 3 or 1000 hertz, okay. So next data, wavelength, that is the lambda, they have given 35 centimeter, okay, 35 centimeter. It is also not in SI unit, but you have to convert that into SI unit. 35 into 10 power minus 2 meter, okay. Now what they're asking, how long will it take to travel 1.5 kilometer? How long means the time they are talking. Okay. So from the motion chapter, okay, from motion chapter we know that speed it is given by, okay, speed it is given by distance divided by time, okay. So here they are asking about a time, therefore a time can be written as distance divided by speed, okay. Speed distance they have given, how much it is? 1.5 kilometers. So here I can write one more data, that is the distance, okay. Distance here I'll write distance 1.5 kilometer, but it is not in SI unit, therefore you can write 1500 meter. 1500 meter, okay, 1500 meter. Now simple calculations. So first what you need, distance you have, speed you need to calculate, speed of the wave. By this equation you can calculate. How? V is equals to frequency, that is 2 into 10 power 3 into wavelength, that is 35 into 10 power minus 2, okay. So V is equals to, and this is 2 into 35, that is 70 into 10 power 3 minus 2, it becomes 70 into 10 power 1. So speed becomes a 700 meter per second, okay, 700 meter per second. And here directly you can substitute the values. Distance is 1500 meter divided by 700, okay. So here you can see 0 0 get cancelled, so 15 divided by 7, and so on. So directly you can write time, it is 2.1 second, okay, 2.1 second, right? Now next question, reflection of a sound. Reflection of a sound, okay. So you may have heard reflection. Reflection means bouncing back, okay. So just imagine you are in a new building, okay. So if you say something, the sound will reflect, nothing but echo. Or else if you are traveling in a forest, okay, if you are in a forest, hillside, okay, if you say something, the same sound will be echoing, okay. So that means the reflection of a sound. So reflection of a sound is nothing but bouncing back of a sound wave. Simple, okay. So in our day-to-day life, we can observe this reflection of a sound, okay. The first one, the sound heard after reflection from a distant obstacle, such as a cliff, a hillside, wall of the building, edge of the forest. after the original sound has ceased is called echo. So this one only we call it as a reflection of a sound. Okay. So main importantly, this reflection is bouncing back. Bouncing back of sound wave. Okay, right. And what are the conditions for hearing an echo or else a reflection of a sound? Okay, so on what condition? On what condition we can hear a echo? Because in our day-to-day life, if you are in a classroom, okay, you are not able to hear that echo. That is a reflection of a sound. If you are traveling on a straight road, if you say something, that sound will not reflect. Okay, at our home only, let's consider our home only, where if you say something, hi, bye, mom, dad, okay, mother, father, sister, brother, whatever you say, that sound will not reflect. Okay, for the reflection of a sound, what are the condition must be satisfied? Let's see one by one. Okay, the first condition, the minimum distance between the source of a sound or observer and the reflector in a air must be 17 meter in a air medium. Okay, so for example, here there is a ball. Okay, here there is a ball and I am the source of a sound, means I am producing a sound. Okay, hi, if I say hi, the distance between this source of a sound and reflector nothing but I have a considered example of a wall. So the distance between source of a sound and reflector must be 17 meter. Okay, 17 meter or else more than 17 meter. But minimum distance should be a 17 meter. It cannot be less than 17 meter, like 16 meters, 15 meter, or else 10 meter or 9 meter. It should be minimum distance is a 17 meter, and it can be more than 17 meter. Okay, if you have a one question, sir, what if the distance between source of a sound and a reflector is a 20 meter? Yes, of course, you are able to hear an echo. That is the first condition. Okay, second condition, the size of the reflector must be large enough as compared to the wavelength of the sound wave. Okay, so if we consider a reflector, here I have considered a wall, right? Wall. So the size of that wall is way bigger than wavelength of a sound, right? So wavelength of a sound in terms of a millimeter or centimeter, but the size of the wall, it is in terms of a meter, right? It is more than a wavelength of a sound. Therefore, I can hear an echo. Okay. So first condition, distance between source as well as a reflector must be 17 meter, and size of the reflector must be greater than, compared to, okay, must be greater than a wavelength of a sound. That is the second condition. And third condition, the intensity of a sound should be such that reflected sound reaching the ear is sufficiently loud to be audible. Okay. So first condition, let's say first condition is satisfied, 17 meter distance. Second condition is also satisfied, the reflector size is more than wavelength of a sound. And third condition, if I say hi, hi, will you able to hear an echo? Not possible, because it is not loud enough to reach this sound, the reflector, because this sound will be observed by the medium, that is the air medium. The sound will not reach the reflector and come back. Okay. Third condition, the loudness of a sound should be sufficient so that the source of a sound, okay, if I produce a sound, that the sound should reach a reflector and come back. That means echo. Okay, and the loudness of the sound should be a sufficient. Okay, right. So these three conditions are for hearing an echo. Next one, reverberation of a sound. Okay, reverberation of a sound. What is this, the reverberation of a sound? Generally, you'll be just imagine in an auditorium. Okay, reflection of a sound, already we know that, right? Reflection of a sound, nothing but bouncing back of a sound wave. And what if the same sound, if I say hi, that a hi will come back, so that we call it as echo. If I say one time hi, the reflection, hi, 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 hi. It is a multiple reflection. This multiple reflection, we call it as a reverberation of a sound. Okay, reverberation of a sound. Multiple echo or multiple, reflection of a sound, we call it as a reverberation of a sound. Simple. Okay. Now, according to the definition, okay, textbook definition. So here you can see a sound created in a big hall will persist by repeated reflection from the walls until it is reduced to value where it is no longer audible. If I say hi, okay, if I say hi, 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 like that. So this is a multiple reflection. It will be audible till that original sound ceases, means it keep on decreases. Okay, persist by repeated reflection from the walls until it reduces to value where it is no longer audible. Okay, and this repeated or multiple reflection, this is the definition. Okay, this is the definition that result in a persistence of a sound is called reverberation. Is called reverberation. Got it? And uses of this multiple reflection, echo, multiple echo. Where do we use? The best example is doctor's stethoscope. Okay, doctor's stethoscope. It works on the principle multiple reflection. Okay, so first example you can see megaphones. Okay, so megaphones are loud hailers. Okay, so generally if consider there is a large gathering. Okay, large gathering. So the police van comes into that particular area and they'll start announcing through the megaphones. Okay, so loudness of a sound will be large enough, and also this takes place in a multiple reflection of the sound. Okay, so here you can see megaphones, horns, musical instruments such as the trumpets and shannais are all designed to send the sound in a particular direction without spreading it in all the direction. Okay, so that should go in a particular direction, it should not go in all the direction. That's how all the instruments here mentioned designed. Okay, and the second application, okay, this is the first application, and the second application, nothing but use stethoscope. Stethoscope. Stethoscope is an medical instrument used for listening to the sounds produced within the heart, within the body. Okay, chiefly in the heart or lungs. Okay, so stethoscope is used to hear a sound within the body. Okay, in the stethoscopes, the sound of the patient's nothing but a heartbeat reaches the doctor's ear by the multiple reflection of the sound. This is the one of the main use. And the third one, okay, third use, stethoscope is a medical. Okay, this is a repeated one. Okay, ignore this. This is a repeated one. And here we have one more example, that is a exercise or example from NCERT textbook. The question says a person clapped his hands near a cliff and heard the echo after 2 seconds. What is the distance of the cliff from the person if the speed of a sound v is taken as a 346 meter per second? Okay, so let's consider this is one cliff and this is one more. Okay, one more cliff, and this is a basement. Okay, distance between okay, distance between here to here, distance between here to here. Okay, let's consider a d, general case. Okay, let's consider a d, and there is a sound. Okay, source of a sound. Let's consider this is the source of a sound. This is the source of a sound, the source of a sound. Okay, the sound will travel this cliff and come back. Okay, so that means this is one way and this is the second way. So that means the sound produced by this person has to reach the other cliff and come back to the same position. Okay, so that is the D. And velocity or speed of the wave, let's consider V. and in the same way it is coming back. Speed of the wave. And here to come back, okay, so time taken from here to here and here to here, let's consider a t. Okay, now what they're asking, what is the distance? See, according to the speed definition, okay, according to the speed definition, that is the distance divided by time, right? Distance divided by time. Here speed I have considered, that is a v. Okay, that is the v. Now here is the distance from, let's say this is a and this is the b. So from A to B, what is the distance? That is the d. Okay, that is the d. And from B to A, again a d. And a time, that is the d. T. That therefore 2d divided by t. And here they have asked the distance, therefore rearrange this equation. D is equals to Vt divided by 2. That equals to V, what is the value? 346 into time, that is the 2 second divided by 2. Okay, and 2 get cancelled, and finally distance is 346 meter. 346 meter. Simple one. Okay, simple calculations, nothing else. Okay, and this is the formula, original formula. Okay, for a reflection, this is the original formula, 2d divided by t. Okay, this is the original formula, and please note down. Very important formula. Very important formula. Okay, now let's move on to the next concept, that is we hear a sound through ear. Okay, this is not required, but as a human being, okay, by which part we can hear a sound? So that is ear. Okay, so first one, here you can see the diagram and the process how we are able to hear a sound. Okay, so this concept you will be learning in biology. Okay, you'll be learning in a bio. You'll be learning in detail in a bio. Okay, right. So here you can see the shape of the outer part of the ear is like a funnel, and the next one, the eardrum is like a stretched rubber sheet, and the sound vibration make the eardrum vibrate, means here, okay, inside the ear. The eardrum sends a vibration to the inner ear. From there, the signal goes to the brain. So in the brain, the process takes place, and you are able to hear a sound. Okay. So this is this concept you'll be learning in detail in a bio. Okay. Now the last concept, that is a range. That is range of hearing. So as a human beings, we are not able to hear all the type of a sound. Okay, all the type of sound we are not able to hear. Okay, like a earthquake. But before earthquake only, some animals able to sense it. Okay, what is the reason behind it? That is the sound. Okay, with the help of a sound, few animals able to sense there is a something dangerous event going to happen. But as a human being, we are not getting it, right? So what is the reason? That is the sound. So range of hearing. Based on range of hearing, so different animals have a different range of hearing. Okay, let's see. So based on range of hearing, here we have three types. Okay, that is the mainly depends on velocity, frequency, and wavelength. Here we are talking about a frequency. Based on a frequency, here we have three different types of a sound. One is infrasonic, second one sonic, third one ultrasonic, or else vice versa, ultrasonic, sonic, and infrasonic. Let's see what are those. Okay, so this ultrasonic, sonic, and infrasonic are the types of a sound based on a frequency. Now here you can see the diagrams. Okay, here elephant and monkey, and the next one here cat and a dog, and here a dolphin. Okay, bat and dolphin. So here you can see infrasonic, human, okay, and next one ultrasounds. So first one you see frequency. Frequency less than, okay, frequency is the less than. Based on frequency, okay, we are differentiating, sounds. If the frequency is less than 20 hertz, can't detected by human eye, ear. The frequency, okay, if the frequency nothing but it is the number of vibration made by the particle. If the frequency is less than 20 hertz, okay, as a human being, it is not detected by human ear. then it is called infrasonic. Okay, it is called infrasonic. If the frequency is less than 20 hertz, we call it as a infrasonic. And greater than 20 hertz and less than 20,000 hertz. Try to understand. Greater than 20 hertz and less than 20,000 hertz. Between this range, 20 hertz to 20,000 hertz. It is called a sonic. Why do we call it as a sonic? Sonic means audible. So, as a human being, okay, this sound can be detected by the human ear. Okay, human ear can be detected this range of a sound. That is the frequency of 20 hertz to 20,000 hertz. Okay, so this one we call it as a sonic. And after 20,000 hertz means greater than 20,000 hertz, it is called ultrasonic sound. Ultrasonic or ultrasound. Okay, this sound also cannot detected by human ear. Okay, three types. So first one, you see these terms are very, very important. Okay, so frequency higher than 20,000 hertz. So also the human ear cannot detect. Okay, these two terms. Next one, human audible range is 20 hertz to 20,000 hertz. This one we call it as a sonic. Okay, this is the sonic range. This is sonic range. Okay, and the next one, infrasonic. Infrasonic means sound waves that frequency is less than, okay, this is the less than 20 hertz. Less than 20 hertz. Less than 20 hertz. Next one, ultrasonic. Ultrasonic, it is nothing but greater than 20,000 hertz. Okay, greater than 20,000 hertz. So there are three types of a sound: ultrasonic, infrasonic, and sonic. Infrasonic means less than 20 hertz, and ultrasonic means greater than 20,000 hertz. Between this 20 and 20,000 hertz, we call it as a sonic. So this sound range can be detected by human ear. Okay. Now, next one, application of ultrasound. Okay. So ultrasounds are high frequency waves. Okay. Ultrasounds are high frequency waves. Ultrasounds are able to travel along defined path even in the presence of obstacles. Ultrasounds are used extensively in our industries and for a medical purpose. Okay, where do we use? Industrial and medical purpose. What is the reason? Because these ultrasounds have high frequency waves and able to travel along well defined path even though if there is obstacles. Okay, and here another use of this ultrasound, that is use of echoes by bats, dolphins, and fishermen. Second one, uses of echoes by sonar. Uses of echoes in a medical field like a stethoscope and ultrasound. Next one, shaped parts, electronic component. Okay, example, okay, here they have given used to clean parts located in a heart to reach the place. For example, spiral tube, odd shaped parts, electronic components. Okay, this point is very important. Fourth point and fifth point. Okay, so this is the fifth point. Okay, so this is the fifth point. Ultrasounds can be used to detect the cracks and the flaws in the metal blocks. Okay, so working principles and all, it is not required. It's just applications of ultrasound you need to learn. Okay, and echo also. Okay, so this is all about applications of sound. Application of sound. Okay, and after the lecture, after completing this video, what you need to do? Revise entire lecture. Revise entire lecture. Then highlight important concept or questions. And third one, note down your doubts in the notebook if any. Okay. After completing all the chapters in a class 9th physics, what you need to do? Revise all. Okay. Revise. Okay. Here I'll add revise all the chapters. Revise all the chapters. Okay. Revise all the DPP. Okay, DPPs. Okay. So If there is any questions or any doubts, you can note down in your notebook. So I'll be coming in a doubt session. Means if you have any doubts, I'll be clarifying in a live. Okay, that is a YouTube live. Okay, so during that YouTube live, you can ask any type of a question related to 9th class physics. Got it? Okay, so that's all about class 9th syllabus with respect to physics subject. Okay, so what do you have to do? So 5 points are very important. Revise today's lecture. Okay, and you have to revise all the chapters in a class 9th physics, and you have to revise all the DPPs that I have given. Okay, so revise, 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 keep revise. That's all. Okay, so that's all for this session, and we'll meet you in the next session. Till then, take care. Bye bye.